Hello and welcome to your mathematics class. In this class we'll be talking about number system. So we will be talking about real numbers. Because there are certain sets in which only real numbers are included. For example, if I say this is a set 1, 2, 3, 4, 5, 6, 7 and it goes on and on forever. So this is a set of natural numbers. And natural numbers are nothing but real numbers. In a similar way, I can say this is a set of whole numbers. Starts from 0, 1, 2, 3 and so on. This is a set of whole numbers. In a similar way, there is a set of integers. Starts from minus infinity, goes on minus 3, minus 2, minus 1, then 0, then 1, 2, 3 and so on. Goes up to plus infinity. So all of these things are nothing but real numbers. So let us study what are real numbers. Real numbers are those numbers which are real by definition. So in each and every scientific application or in each and every application that you involve in your day-to-day life, you deal with real numbers. For example, you purchased 2 kilograms of sugar. You purchased 2 kilograms of sugar from a shop. So this 2 is a real number. Suppose you then purchase 2.5 kilograms of sugar. Then this 2.5 is a real number. So every number that you deal in your day-to-day life, these are all real numbers. So real numbers are everywhere. For example, in your meter reading, in your voltmeter reading at your home, you read 220 volts. This is a real number. And your frequency is suppose 50 hertz. This is 50 is a real number. Suppose the reading changes to 222.56. This is again a real number. So every number that you encounter in your day-to-day life is nothing but a real number. So today we are going to discuss about real numbers, and let us see how many sets you can make out of real numbers. So by pictorial representation, a real number line is represented by a straight line like this, and in this straight line we have included all the possible real numbers here. So 0 is the middle position, then you get 1, 2, 3, 4 and so on. In a similar fashion, in the negative direction you get minus 1, minus 2, minus 3, minus 4 and it goes on up to minus infinity and it goes on plus infinity. So each and every number, each and every point in this number line is a real number. Now the beauty of real number system is that between any two numbers there are infinite number of numbers possible. For example, if this is 1 and this is 2, then in the midpoint we have 1.5. This would be 1.5. If this is 1 and this is 1.5, then you have some number in the middle, then you have another number in the middle, and you can go on and on so forever. So between any two numbers there are infinite number of numbers possible. Let me show you. If we select 1 here and we have 2 here, what is the midpoint here? 1.5, right? So 1.5 stays in the middle. Now what is the midpoint of 1 and 1.5? There is some number in between 1 and 1.5. Then you take this number and you include it here, then you will have some number in the middle. So each time you try to get in the middle position, it becomes smaller and smaller and smaller and smaller and smaller and so on. So that means in each and every position there are infinite number of real numbers possible. So each and every point in this number line is a real number. Now keep this in mind that there is another number line possible, and that we call an imaginary number line, and that exists perpendicularly at 0 position. But in your syllabus, in this chapter, we will not discuss about this line. What is that number line? We call it the imaginary number line. Starts with I, then 2i, 3i, 4i, and in the negative direction it is minus I, minus 2i, minus 3i. Beauty of this number line is that each and every number is an imaginary number, and imaginary numbers have no physical significance. All the real numbers have physical significance, but the imaginary numbers, they do not have any physical significance, but we do include them in our day-to-day life operation because it makes the calculations easier. The imaginary numbers find applications in various scientific and engineering applications, so they are used there. And this whole plane is known as, some people call it the S plane, Some people like it as the complex plane, or in your complex number chapter sometimes it is referred to as the Argand plane. The Argand plane, it goes by several names, but it means the same thing. But for the time being, let us study about the real number line. Let's study about the real number line. So as I've said before, there are infinite numbers in the real number line. Between any two real numbers, there are infinite number of numbers possible. For example, it starts from 0 and in this positive direction it reaches 1, right? So you can say that here it is 0.1, then 0.2, 0.3, 0.4, 0.5. The midpoint is 0.5, then goes on 0.6, 0.7, 0.8, 0.9, then it reaches the position of 1. So in a similar way, between 0 and 0.1 there is another midpoint, we call it 0.05. So 0.05 is the midpoint between 0.0 and 0.1. In a similar way, you can go for another midpoint between 0 and 0.05. So in a similar way, you can subdivide this interval into smaller and smaller and smaller position, but you will never reach that. So we see that there are so many numbers in the real number line. We represent them with these numbers. So these are the integer numbers 0, 1, 2, 3, 4, 5, 6 and so on. So in the positive direction it goes up to infinity, and there are infinite numbers between any two numbers. If you select any two numbers, between these two numbers there are again infinite number of numbers possible. Okay, so now let us see. So it must be clear to you that this is the real number line. Each and every number that we deal in our daily life, they fall somewhere in this number line, right? Now let us see what is a real number set. The real number set is represented with a capital R. That means capital R is nothing but the set of real numbers. The set of real numbers. So it is the biggest possible set of all the numbers that you deal in your day-to-day life. Whatever number you may receive in your day-to-day life, whatever number your calculator reads, it must be somewhere in this number line. And the set of real numbers includes all the possible numbers possible. Now, how do we formulate sets from real numbers? Now, the first set that we can formulate from the real numbers is nothing but the set of natural numbers. And the set of natural numbers includes all these milestones: 1, 2, 3, 4, 5, 6. So from natural numbers we have 1, 2, 3, 4, 5, 6, and it goes on up to plus infinity. Beware that natural numbers are not in the negative direction. They are always existing in the positive direction. So can you say that the set of natural numbers, capital N, is nothing but a subset of the real numbers? Yes, because every element of this set of natural numbers, they are inside the set of real numbers also. So you can say that the set of natural numbers is a proper subset of the real number system, right? Now we again have the set of integers, set of whole numbers. Set of whole numbers start with 0 and it goes on like this. So you also have a 0 here. Apart from the natural number line, you again have 0 here. 1, 2, 3, 4, 5, and it goes on up to plus infinity. This is the set of whole numbers. You have to keep this in mind that capital N stands for the set of natural numbers. Capital W stands for the set of whole numbers. In similar fashion, capital Z or capital Z includes the set of integers. Starts from minus infinity, then it goes on minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and goes on up to plus infinity, right? So what is the type of representation of the set? This is nothing but the tabular method of representation of natural numbers. Again, this is the tabular method of representation of whole numbers. This is the tabular method of representation of integers. If we try to represent the tabular method of representation for real numbers, it would be somewhat like coming from minus infinity comes to minus 2, then again we put dot dot, then minus 1, then dot dot, then 0, then dot dot, then 1, dot dot, 2, dot dot, 3, dot 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 up to plus infinity. Why do we put dot dot between minus 1 and 0, and here we do not put any dots here or here or here? Because the real, as I have said before, in between any two real numbers there are infinite number of numbers possible, right? So it includes each and every number possible that you encounter, whether it be a decimal number, whether it might be a decimal number somewhat like this, or it might be just a number, or it might be somewhat like this 0.000005. Whatever number you encounter in your daily life, it is somewhere inside this real number line, and each and every number, if you combine it in a set, it becomes the set of real numbers. Then we again have the set of positive integers represented with a z plus or a z plus, whatever you call it, and it will include only the positive integers. Those are 1, 2, 3, 4, somewhat like that. So we see that we can make several subsets out of the real number set, right? Now let us try to relate them using the subset theory. So it must be clear to you that n represents the set of natural numbers, capital W represents the set of whole numbers, capital Z or capital Z represents the set of integers, and so on, right? Now you can see from this set or this collection of set that natural numbers, the set of natural numbers is a proper subset of the real number set. Can we say that the set of natural numbers is a subset of real number set? Yes, because each and every element of this set is present in the set of real numbers. In a similar way, each and every element of the whole number set is also a subset of this. That means each and every element of the whole number set is also present in the real number set, right? So you can say that whole number set is also a proper subset of real number set, right? In a similar fashion, you can say that Z is also a proper subset of set of real numbers. Now can you relate the subset theory in between these sets n, w and z? Can you relate it? Try it. Can you see that w is again a proper subset of the set of integers? W is a proper subset of this set again, because each and every element present here is also present here, right? In a similar fashion, n, the set of natural numbers, is again a proper subset of z. Yes, because each and every element present here is also present there. So you can go on and relate them using the subset theory. But the most important thing here to notice is that capital R represents the set of real numbers, capital N represents the set of natural numbers, capital W represents the set of whole numbers, and capital Z represents the set of integers. You have to keep this notation in your mind forever. Now let us discuss some sets which are called intervals. So this must be clear to you, right? Let me rub it out now. In our next slide, we will see certain sets that we call them as intervals. We call this set as intervals. Let me first draw the real number line again here. 0, 1, 2, 3, plus infinity, minus 1, minus 2, minus 3, goes up to minus infinity. So this is the real number line, right? Now if we represent a set so that it lies in between these two numbers, that means the set of all numbers that lie between minus 1 and 1, if we say there is a set which includes elements, those are numbers, and these numbers lie between minus 1 and 1, then we say that this is nothing but an interval. interval that exists between these two milestones, that is -1 and +1. Now accordingly there can be several types of intervals. Let us see what are those intervals. If we say that let A and B are any two real numbers. If we say that this number A and this number B are any two real numbers, that means A might be here and B might be there, suppose, for example, then we can represent one of the sets like this. For example, consider this set, the set of collection of x's such that x is a real number and x is between A and B. Can we call this a set? Yes, because this is nothing but the set builder method form of representation of a set, and it is saying that it is a collection of x's which are real numbers and this x exists between A and B. So A is a point here and B is another point on the number line, and all of the x's that are existing between A and B, so all the numbers that are between A and B, that means that includes -2, -1, 0, 1 and again this point B, and all the decimal numbers that are in between A and B. It includes all the numbers in combined fashion, but it excludes A. So A is not present and B is not present. Why? Because x is greater than A. X is not equal to A, but x is greater than A. In a similar fashion, x is not B, it is less than B. So it does not reach this A and B position, but instead it lies somewhere in between these two numbers. Such a set we call them as an open interval. It has a special name, we call it as an open interval. We call it an open interval. And there is a special notation we use. If the boundaries, these are known as boundaries, if these boundaries are A and B, then we like to represent it using this type of symbol. Okay, now let us see what is a closed interval. If this is an open interval, if an open interval looks like this, then what a closed interval would look like? It would be a collection of x's such that x belongs to the set of real numbers and x is between A and B with A and B included. Now such a set we call it as a closed interval. We call it a closed interval. Why do we call it a closed interval? Because not only does it include all numbers between A and B, but it also includes this point A and this point B also, right? Because we are seeing that x is not only greater than A, but x is also equal to A. In a similar fashion, x is not only less than B, but it also is equal to B. So it is clearly including these points A and B, but here this is excluding the points A and B. This number system, this x collection of x's here, all of these x's do not contain the number A, right? They do not include this number A or the number B, but they lie in between A and B. So we call it an open interval and we call it a closed interval because it is including the numbers A and B. So we represent this interval with this type of notation. See, the bracket is closed, this bracket is closed, but this bracket is left open in order to represent this as an open interval. Here the brackets are closed, so it represents a closed interval. And if we again represent this set like this, here A is left open, this boundary is left open, but this boundary is closed with an equal sign, and in a similar fashion I can do that for B also. Then both of these sets are called as semi-open or semi-closed intervals. You can either call it a semi-open interval or you can call it a semi-closed interval. So this set, how can you represent using this type of notation? See, this A side is left open, so you have to use this open type of bracket on the A side, and the B side is closed by an equal sign, so you will use the closed brace here. So this represents this semi-open or semi-closed interval, and for this set you will represent this, the A side is closed, so you will use a closed brace here, but the B side is left open, so you will use the open brace there. So we are seeing that intervals are certain sets in the number line, real number line, which are bounded by certain milestones or positions, and the numbers existing between these two numbers are considered in the set, right? So if you are excluding these two milestones, this A and B, these two numbers, if you are excluding them, you are not including them, then we will call it an open interval. And if you are including them, you will be calling them as a closed interval. You will represent it using this closed type of bracket here. Here you are leaving this bracket open. While in semi-open and semi-closed interval, you can represent it in this way for this set, and for this set where there is an equal sign which closes the set at this position but it is left open on the other side, so you will use a closed bracket here, but you will leave this side open. So here we are seeing that there are 4 types of intervals possible. These are all 4 types of interval. And there is another theory, you will keep it in mind, that if you subtract the limits, that is b minus a, that means the numbers existing between A and B, if you take the difference of these two milestones or these two boundaries, then you can call it the length of the interval. This is known as the length of the interval. This is known as the length of the interval, right? Length is nothing but the distance between A and B. Okay. Now sometimes it is required in your question that you represent it using a number line. So in that case, for example, if A and B are two numbers in the number line, you will say this is a number point A, this is the point B in your real number line, and all the points that exist in between A and B are included in this set, right? Now if this is an open interval, you will represent using this. However, in this case this is a closed interval, right? So the interval exists between A and B, and since these numbers are included, so in that case you have to encircle these two endpoints. This circle indicates that these 2 points are included inside your set. See, these 2 points are included, so that's why you have mark them using these circles. For this set, what will you draw? How will you represent this set? For this one, these endpoints are A and B. Now here you are seeing that this point is excluded, right? So you will not draw a circle here, but this point is included. That means you will draw a circle here. That means all the points between A and B along with this circle point B are included inside this set. And in a similar way, if you represent it for this set, here we will include the point A and B and all the numbers in between along with this number A also. So this number A is included along with all the possible numbers between A and B, but you will not include B because B is excluded here. In this case, A, all the numbers you will consider along with this point B, but you will not include this point A because A is not included here. In a similar way, here you will include all the points between A and B. Okay, and you will also include this point A as well as point B. In this case, you will include all the points between A and B, but this A and B are not included. So it must be clear to you how to represent an open interval either by this notation or by this notation. In a closed interval, you can use this type of notation or you can use this number line diagram. For semi-open or semi-closed interval, you can use these type of symbols. Okay, now let's move on to some standard intervals. So let me rub it out now and show you some standard intervals that we know they exist. So now it must be clear to you what are intervals. There are 4 types of intervals, as we already know. Now let us look at some standard intervals that we use. Standard intervals. Look at this interval, minus infinity to 0 with 0 included. Now in the number line, this would mean all the numbers that are existing between 0 and minus infinity. Minus infinity is not having any point because minus infinity is not a number, it is just continuation forever. So minus infinity itself is not included, but it includes all the big negative numbers along with all the numbers existing in this point up to 0, and 0 is also included. So here you will have minus 1, minus 2, minus 3 and so on, and each and every point on the number line, they are also included in this set. So as you can see, from a number line, one of the numbers is 0, then we have all the positive numbers, so these are all positive numbers, and here you have all negative numbers. All numbers existing in this fashion are negative, all numbers existing in this direction are all positive, and 0 here is neutral. 0 here is a neutral number, it is neither positive nor negative. So if you look at this set which is represented in this number line, what will you name this set as? See, 0 is neutral, and rest all the numbers are negative. All the numbers are negative. So you include one neutral number and all the negative numbers possible in this set. So this set should be named as the set of non-positive. Can you say that this is a set of non-positive numbers? Yes, because you can see that all the elements of this set are not positive. That means some of them are negative and just one of them is a neutral number. So definitely 100% sure fact is that all the numbers are definitely not positive. So we call this set as the set of non-positive real numbers. Since it is existing between two limits, we are calling this special set as a interval, and this is a standard interval between minus infinity to 0. Let us look at another example. Another standard interval that we like to use goes from 0 to plus infinity. What we will call this interval as? See, this includes 0 and all the numbers up to plus infinity, all the numbers. So here is 1, 2, 3 and so on. So you can see that all the numbers are positive and 0 is neutral. So what is the sure and certain fact about all the numbers? The sure and certain fact about all the numbers is that each and every element in this set is a non-negative real number. So you can call this set as the set of non-negative real numbers. In a similar fashion, there is another standard set, minus infinity to 0. This time it is an open interval. Here 0 is not included. Here 0 was included. Here we have excluded the 0. So if you look at the number line, it is coming from minus infinity up to 0, but 0 is not included. Minus 1, minus 2, minus 3, all the points are included, excluding 0. So we are seeing that all the numbers are nothing but negative. All the numbers are negative, and 0 was neutral, right? So, but we have not included 0 here. So that means the set containing all the negative real numbers. So we'll call this as the set of negative real numbers. And again we have another set 0 to plus infinity open interval. Look at this one. Here we have 0, here we have 0 and it goes on up to plus infinity, and here we have plus 1, plus 2, plus 3, plus 4, but 0 we have excluded as an open interval, so 0 is not here, not in this set, but all the numbers that are positive are included. That means each and every element in this set is a positive number. So this interval is nothing but the set of positive real numbers, positive real numbers. And finally we have a set open interval minus infinity to plus infinity. What is this set? It comes from minus infinity and it goes on up to plus infinity. That means all the numbers existing between minus infinity and plus infinity. What is this set? Here we will have 0, here we have negative numbers, here we have positive numbers, we have obviously included 0. That means it is a combination of the negative real numbers, the 0 along with all the positive real numbers. Then what do we call this set? Yes, this is the set of the entire set of real numbers. So this is nothing but the set of all real numbers. So these are 5 standard intervals that we include in our discussion today. So now let's solve some problems on intervals and see how do we represent certain sets as intervals. Let's write a question. Write the following sets as intervals. The first example is a collection of x's such that each x is a real number and x is between 4 and 20 and x can be equal to 20. But x cannot be equal to 4 because x will always be greater than 4. X can be less than 20 or x can be equal to 20. That's why. Now, if you represent this set as an interval, which the question is asking you, then you will represent it. First, write the limits. Minus 4 and 20 are the limits. And since this is an open interval, so you will leave a open bracket here. But 20 is included, so we will close the bracket here. So this is the answer represented as an interval. This set is represented as an interval in this fashion. Let's look at example number 2. A collection of x's such that each x is a real number and x is existing between minus 20 and minus 10. So this is a set of real numbers where the numbers are between minus 20 and minus 10. But minus 20 and minus 10, these two numbers are excluded. So this obviously is an open interval and you will first write the limits minus 20, minus 10, and you will leave this bracket open because there is no equal to sign here, and you will leave this bracket open as well because there is again no equal sign here. Okay, so this is an open interval, this is a semi-closed interval. Next, another example. Collection of x's such that x is belonging to the set of real numbers and x is between 2 and 15 with 2 and 15 included. So this obviously is a closed interval. So first write the limits 2 and 15, and since this 2 is included, so you will close the bracket. Since this 15 is also included, you will close the bracket here. Let's look at example number 4. Example number 4. Collection of x's such that x belongs to the set of real numbers and x is between minus 8 and 25, with 25 excluded but minus 8 included. So how to represent this set as an interval? First write the limits minus 8 and 25. Since 25 is excluded, leave the bracket open. Since minus 8 is included, close the bracket. So this is as simple as it is. Very simple mathematics here. Okay, now it must be clear to you how do you represent some sets as intervals. Now let us go in the reverse fashion. Let us represent some intervals as sets. Write the following intervals as sets in set builder form. Number 1, let us try to represent this interval minus 3 plus 5. So this is an open interval. How will you represent this as a set in set builder method? You will say this is a collection of x's such that x is in the real number line, and since this is an open interval, so you will have to write minus 30 here and 5 here, and x will exist between minus 30 and 5, but minus 30 is not included, as well as plus 5 is also not included. So you will not write an equal to sign here, but x is existing between these numbers. Okay, move to question number 2. Try to represent this as an interval. Try it. It will be a collection of x's such that x belongs to the set of real numbers. Write the limits, and x is between 2 and 8, but 2 and 8 are also included, so you will write an equal to sign here and you will close the bracket. So this is a set in set builder method or set builder form, such that this interval is represented in the set builder form. Let's move to question number 3. Try to represent this set in the set builder form. Semi-open interval 7, 18. This will be collection of x's such that x belongs to the set of real numbers, and x exists between 7 and 18. 7 is included, so there is an equal to sign. 18 is excluded, so there is no equal to sign here. In a similar fashion, try to write this one at your home. Minus 7, 0, semi-closed interval. Okay, so now it is clear to us what is an interval, what are real numbers, and how do we represent the set of real numbers, how do we represent natural numbers, whole numbers, integers, and so on. Now at this position we move to a new topic. We are calling it an universal set. Let us try to learn what is an universal set. If we define an universal set, it is the largest possible set in any particular discussion. This is just a simple definition. Let me explain to you what it actually means. For example, if we say that n is a set of natural numbers, okay, so you are giving me one set that is a set of natural numbers. In the same discussion, somebody else gives another set, suppose the set of whole numbers. Set of whole numbers. Again another person comes, gives another set, the set of integers. Now in this discussion we have three sets, the set of natural numbers, the set of whole numbers, the set of integers. Then tell me a set which is the master of all these sets. That means which is the largest possible set in this discussion. What is this discussion about? The discussion is about numbers. See, this is discussing numbers. Integer is nothing but another number. So all of these are numbers. All these three sets are discussing about numbers. So what is the biggest possible set of numbers? The biggest possible set is the set of real numbers. Right. So you were discussing about numbers. So what is the biggest possible set that you can think of? The biggest possible set will be the set of real numbers. So this is the set of real numbers, and it is the master of all these sets. So universal set is the largest possible set in any particular discussion. So here we have a discussion of three sets here, and all the three sets are discussing about numbers. So what is the biggest possible set that you can think of here in this particular discussion? Yes, the biggest possible set would be the set of real numbers. So each and every set is made out from the set of real numbers. So the biggest possible set, or you can say that universal set in this particular discussion, the universal set is the set of real numbers. Let me give you another example. Let us create another discussion here. Let us say B is the set of boys in class 11 of your college. Let us say this is B1. Let us give G1 another set, the set of girls in class 11. Somebody comes and gives a set B2, the set of boys in class 12, and G2, the set of girls in class 12. So this is a particular discussion with four sets, right? So what is the biggest possible set in this particular discussion? See, all of the set are discussing, this set is discussing about boys, this is discussing about girls both in class 11, here boys and girls both in class 12. So what is the biggest possible set in this discussion? The biggest possible set would be, yes, obviously the biggest possible set would be the set of students, the set of students in your college. See, each and every set is nothing but a subset of this master set, that is the set of students in your college. So in this particular discussion with four sets, the set S, which is the set of students in your college, will be the universal set. Let me give you another example. For example, let us say A1 is the set of people living in your state, for example Assam. Okay, let us say W1, the set of people living in, say, another state, West Bengal. In a similar fashion, let us say D1 is the set of people living in Delhi, and so on. I can give you several sets like this. But in this particular discussion, can you tell me the biggest possible set? The biggest possible set obviously would be the set of people living in your country, because country includes all states. Okay, so you will say that I is the set of all people living in India. See how simple it is. So this is the universal set in this particular discussion. Universal set is the largest possible set in any particular discussion. So this is a particular discussion, and here in this discussion we are discussing about people living in a particular state. So this is one state, this is another state, this is another state. So I would be the set of all people living in the country, because country is including several states, and if we are having all the sets representing people in a particular state of that country, so the people living in that country would be the universal set in that case. So we have learned what is a universal set. And here we have a point: universal set is represented with capital U. We always like to represent the universal set with the capital U alphabet of the English language. Okay, so universal set is always represented with a capital U. So you can say this is capital U, the universal set in this particular discussion. Okay, now so this must be clear to you what is a universal set. Let's move on. Let's move on to another topic. We call it the Euler-Venn diagram. Euler-Venn diagram. Now this is a very beautiful diagram that represents a set or a collection of sets inside the universal set. Now Euler is a mathematician, Venn was another mathematician. They combined their theories into a combined diagram, and it is known as the Euler-Venn diagram. Remember to pronounce this as Euler, not Euler. Euler is the correct pronunciation. So Euler and Venn, they devised a diagram to represent sets. So let me just give you an idea what would be an Euler-Venn diagram. Let us say we have a set A is equal to 1, 2, and let us say we have a set B is equal to 2, 3, 4, and let us say that we have a universal set in this particular discussion. Let us, for example, say this universal set is 1, 2, 3, 4, 5 and 6, for example. So remember here that there is a point to be remembered. Universal set U is represented with a rectangle. In the diagram, universal set is represented with a rectangle. So let us say we have a rectangle here, and this represents the universal set U. Inside this universal set, we will have some numbers, and these are nothing but the elements of the universal set. So each and every element is represented with a dot. So 1 is an element represented by a dot, 2 is another element represented by a dot, right? Let's write this 2 here, dot 2. Okay, then we have 3, we have 4, we have 5, we have 6. So we see that we have 1, 2, 3, 4, 5, 6, just like we have written here 1, 2, 3, 4, 5, 6. So each and every dot represents an element inside the universal set. Now again we are having a set A containing 1 and 2. So any set that is inside the universal set is represented with a circle, and this circle represents the set A. See, A has elements 1 and 2. So in this circle we have 2 elements. Inside this circle we have 2 elements 1 and 2, and we represent this set with a circle A, right? Then we have the set B. Where is the set B? B is including 2, 3 and 4. So let's write it here, 2, 3 and 4, and this is the set B. Okay, so the set B is having 2, 3 and 4 inside this circle. Inside this circle we have elements 2, 3 and 4, and in this circle we have elements 1 and 2, just like what we have written here. And these 5 and 6, they are not a part of this A and B. See, 5 and 6 are missing here, 5 and 6 are missing here, but the 5 and 6 are included in the universal set. They are still inside the rectangle. That means each and every dot is a part of universal set. See, 1 is a part of universal set, 2 is a part of universal set, 3 is a part of universal set, 4, 5 and 6 are also parts of universal set, just like we have written here. But inside this they are also subdivided. 1 and 2 are also parts of A, also part of the set A, and 2, 3, 4 are also part of set B, and we represent each part with a circle. So each of the circle is a set. Okay, now this entire diagram is known as the Euler-Venn diagram representation of sets. So a set can be represented in 3 ways we have seen. First method is the tabular method, second method is the set builder method, and the third method is the Euler-Venn diagram method of representation of a set. It includes a universal set as well. So universal set is represented with a rectangle, and all the sets will be inside this universal set. No set will be existing outside the universal set, because by definition the universal set is the largest possible set. So all the sets that you have here will be the smaller versions or the smaller parts of the universal set, and they will exist as circles inside the universal set. Let us give another example. Let us look at another